Hello and welcome to a new very interesting video. This video is about the simplest operational amplifier in the world. So these things here are operational amplifiers, and if you build electronic circuits then you might have already used some of these to build a circuit, okay? And these things are pretty easy to use actually, but they contain highly complex circuits. So this operational amplifier, for example, this is the famous LM741 operational amplifier, and the inner circuit of this one is this here, okay? So it is quite complex. It contains 20 transistors, and yeah, so it's quite complex circuit in here. And we want to build the simplest operational amplifier, and we will build it with discrete components with just transistors like this one. But the question here is, how many transistors do we need to implement the basic function of an operational amplifier? So if we reduce the amount of transistors, then maybe the characteristics of the final device won't be as good as the integrated solution with so many transistors here. But for some applications it can be beneficial, because maybe it has less noise, or maybe it's just enough for this application and you don't need an integrated circuit with so many components in it. Okay, so but now the question is, how many transistors do we need to implement an operational amplifier like this? So how many transistors do we actually need? Is this enough? Or do we need more? Do we need less? How many do we need? So take your guess right now and I will tell you the answer. The answer is pretty simple. We can remove these transistors, this one, and also this one. So there's only one left. So we need only one transistor to implement the basic functionality of an operational amplifier. So the disclaimer here is it won't perform as good as the real operational amplifier, of course. There are many properties in which this one is much better than the operational amplifier which we are going to build out of one transistor, okay? But it is possible to get at least the basic functionality of an operational amplifier with one transistor. And in this video I will show you how this can be done. Okay, and before I will show you the final circuit, which is actually pretty simple, I will show you a little bit of theory so that you know how everything comes about. And after that I will show you the final circuit on the breadboard and we will measure how well it performs. Okay, so let's start constructing our operational amplifier. But before we can start building our own operational amplifier, we have to review the basic concepts of an operational amplifier so that we know what we are going to build, right? So let's do that. So first of all, let me draw the symbol of an operational amplifier, which is just a triangle, and then we have two inputs, a non-inverting input and an inverting input, okay? So let me make them the same length, there we go. And then of course we have an output, which is this one here. Alright, so since our operational amplifier is an amplifier, it needs some sort of external power supply. So it has to amplify something, so it needs an external power to amplify things. So the input power is less than the output, so it needs some additional power, and therefore it also needs a supply voltage, maybe plus and ground or plus and minus supply. And the thing with this is that in circuit diagrams this is very often neglected, so they don't draw this plus minus supply, and maybe they draw an extra box which has a plus minus supply and it belongs to the operational amplifier or something. But keep in mind that even if it is neglected, it needs to be there. An operational amplifier won't work without an external source of energy. So every circuit diagram which does not contain these two connections has to, the operational amplifier has to have these connections, otherwise it won't work. It's like the filament of a tube. So if you have a vacuum tube, vacuum tubes have filaments, and sometimes in circuit diagrams this filament is neglected and you just draw the tube, but you have to know that you need the filament, because without the filament nothing will happen. So here this is the same. Alright, So let's see what this basic structure, what this basic operational amplifier does. So first of all, let me connect two input voltages. I call this input voltage of the non-inverting input, I call it V in 1, and it goes from here to ground. And the input of the inverting, the voltage of the inverting input, I call it V in 2, okay. And we have an output which goes here, which is V out. Alright, so there we go. And what is the how is V out related to the input voltages? So let's see if we can get a simple equation for that. So we need V out is equal to something. And what is this? The operational amplifier is some sort of differential gain, so a gain of the difference between these two inputs, and I call this now just A1. So this is some gain, and it's the gain of the difference of these two inputs. So the difference of these inputs is pretty simple. It's just V in 1 minus V in 2. Alright, V in 1 minus V in 2. So our output is pretty simple. It's just the first input, the non-inverting input, minus the inverting input times the amplification gives us the output. So this is the basic functionality that an operational amplifier has. It takes two voltages, it subtracts them. So subtraction is the first part, and then the second part is it amplifies it with some gain. In this case I call it A1, and this gives us the output voltage. So this is the basic functionality of an operational amplifier which we have to implement. An operational amplifier has lots of other nice properties. It has common mode rejection. It has a very, very high open loop gain. It has a high input impedance. It has a somewhat low output impedance. It has supply voltage ripple rejection maybe. So it has a lot of nice features, and we want to implement these features in our one transistor operational amplifier because we just have only one transistor. So we have to neglect a little bit of these nice properties, okay, but it will have the basic functionality, which is the subtraction of two voltages, and then it will multiply it with a specific gain. Okay, so before we continue with building our operational amplifier, we have to review something else, and this is a basic transistor amplifier, and in our case it's a common emitter amplifier. And I will tell you a little bit about the common emitter amplifier before we can start building our own one transistor operational amplifier. Okay, so let's clean the board and let's do that. Okay, so before we continue, let's start with the common emitter amplifier. So let's refresh the common emitter amplifier, because we need a solid understanding of the common emitter amplifier to build our simple operational amplifier, or one transistor operational amplifier. And if we have a solid understanding of the common emitter amplifier, then we might already have some clues how to build a one transistor amplifier. So let's start with the common emitter amplifier. So common emitter amplifier means that the emitter of the transistor goes to AC ground, so it's grounded, at least for AC. And it can also be degenerated, so there can be a transistor between here and ground, and in the equation later on we will see what this is doing. Basically it reduces the gain, but we will see it in more detail. So if you want to have the maximized gain, you can short it with a capacitor like this. Okay, then for the operating point of the transistor, we also need some resistors at the base, and on a common emitter amplifier the output is at the collector of the amplifier, and we need to decouple it for the next stage with capacitors like this. I call this resistor RB1 and this resistor RB2 because these are the two base resistors, and I call this resistor RC because it's collector, and this is RE because it's the emitter resistor. Alright, and what we want to know is the gain of the circuit, which I call now AV, and this is what we want to know. And what is AV? AV is the ratio of the output voltage V out divided by the input voltage V in. So this is V out over V in. There we go. And this is what we like to find out with all these parameters right here. Okay, for this we need the small signal equivalent circuit of this, and we need the small signal model of our transistor. And the small signal model of a bipolar transistor is pretty simple. So since it's a bipolar transistor, it has 3 connections, okay? And what do we have to connect between these connections? For the base to emitter junction, we have a resistor in here, which we call R pi. R pi is beta over GM, by the way, so this is how it is computed. So let us put it here. R pi is beta, which is the current gain, over GM, which is the transconductance of the transistor. And then on the other side here we have between the, so this was the base, this was the emitter, so this is the collector, and between the emitter and the collector, we have something else. And what is this something else? It is a current source, because a transistor acts like a voltage controlled current source. So we have to plug a current source into here. And since this is a current source, since no current source is ideal, it will have a parallel resistance here, which is called RO or something like this. And we will neglect this resistor in this video, because it simplifies things a bit, and you can do it with RO. It's not that much complicated, but it is more complicated, so I will do it without. And what else? This current source is controlled by this voltage. So if we call this voltage here, it's even, since this is R pi, I call it V pi. Okay, how big is this current? This current is actually the transconductance of the transistor, GM, times this voltage, this base emitter voltage, and this is V pi. So the base emitter voltage, V pi, multiplied by the transconductance of the transistor, gives us the current. So actually, what is the transconductance? We have also a formula for this. The transconductance, GM, is the collector current, the operating collector current, or the quiescent collector current flowing down here, divided by the temperature voltage, VT. VT is temperature dependent, and at room temperature it's about 26 millivolts. Okay, how does this come about, you might ask? And just a short explanation, but I don't want to get too much into details because then the video will be too long. But if you plot the response curve of the transistor, where we have VBE here and the collector current IC here, so this is the collector current IC, which then flows here, then we have the following characteristics. It's this, it's a bit like a diode, and here we have about 0.6 volts or something, or a bit more here. The slope, since we are using a small signal model, we have an operating point maybe here, and this operating point here, that the signal is moving up and down, but at a relatively low amplitude. So if we get somehow the slope of this thing here, then we can get the transconductance. So if we write this down as a function, which we can, and this is the collector current, this is the simplified formula for this diagram here. The collector current is the reverse saturation current of the transistor times e to the power of VE, which is this voltage, divided by VT, the temperature voltage. And if you take the first derivative of this formula right here, then you get the slope, of course. And if you take the first derivative and plug this formula back into the result, you might end up with this formula right here, okay? And this is how this is derived, okay? But now let's continue computing the gain of this circuit. So we have to connect the resistors. So we have the emitter resistor going to ground like this, okay? For the input, I connect a current source, or sorry, a voltage source, of course, not the current source. I connect a voltage source at the input, the signal source, and this signal source is our generates our input signal, and I neglect the resistance of this source. So this resistance has no output resistance. It's 0 ohms output resistance, so it's a pretty good source. And therefore I can ignore these resistors because they have no loading effect on this source. So I can directly connect it, and since it is an AC equivalent circuit, this capacitor here is a short. So let me draw that. So here we have the source going to ground, and this generates the voltage V in. Alright. So, and this here is ground, so this is connected. I just connected to make things more clear, and this still stays ground. And what else? What else do we have? We have our emitter resistor, and of course, because I haven't mentioned it, if this capacitor is there, then this emitter resistor is shorted. So then it is not in the circuit, because then it's an AC short. So actually for this equivalent circuit, we have to remove this capacitor. So now this here matches this. Okay. So now what else do we have? We have this collector resistor like this. And since it is connected to plus, plus goes to AC ground, because plus is like, you can imagine your voltage source like a very huge capacitor. And a very huge capacitor is a short for AC, and therefore this goes to AC ground. So we can connect it like this. And this here, of course, is the collector resistor. Alright, so on this resistor we have our V out going from here to AC ground. V out, there we go. And this is how we measure our V out, because V out is here, so we have it across here, across this. So this here across here is our output voltage. Okay, so now we have to take care of our currents, because the current here flows in this direction. So the collector current, I use a small I because it's small signal. Here we have the base current. I also use a small I. Let's also use a small B, or no, let me use big B. Okay, there we go. And here we have our emitter current, I emitter. Okay, there we go. And the important thing here to note is that the voltage on the resistor here is in the wrong direction actually, because voltages on resistors are in the direction in which the current is flowing. So this is fine, but this is not fine. So the voltage, actually the voltage across the collector resistor is minus V out. Okay, so we can write an equation for that already. So we can say that V out, this voltage here, is minus RC times and IC. Okay, there we go. So this was our first equation, which we will need to derive the gain for this circuit. And the second equation is just a KVL on this loop here, and this will be pretty simple, because we just can say V in is the sum of these two voltages. So this is our V pi plus, and this here RE is just IE times, so this voltage here is just IE times RE, so IE times RE. Alright, there we go. Okay, so what's next? Now what do we have? We have our output voltage in terms of this resistor. We know the resistor, but we don't know the current yet, but we can get the current with GM if we know V pi. And so I would say let's write an equation for this IC, which contains GM and V pi. So maybe we then can complete the whole thing. So let's see, how big is IC? IC is of course just GM times V pi, right? Because it's this current source, so it's this current here. And we have V pi in here, alright? We have V pi here, so we can get V pi from this equation. And this gives us IC over GM. There we go. So V pi is IC over GM. So we can plug this here into here. And this is V in, this is V out, so maybe we can also already write V out over V in. So V out over V in. What is this now? So alright, there we go. What is V out? V out is minus RC times IC. There we go. And this V in is V pi, so it's IC over GM plus IE times RE. There we go. So now one thing, we have here IC, the collector current, and we have here IE, the emitter current. And how is IE related with IC? Actually, we have the current flowing through the emitter here is actually the sum of the collector current plus the base current. And the collector current is beta times the base current. So we can write the equation that our IE is equal to the collector current IC times 1 plus 1 over beta. Okay, because the emitter current here is the collector current, so we have this 1 IC times 1, so we have this 1, and then we have 1 over beta because IC over beta gives us the base current, and therefore we have here we have the base current, here we have the collector current, and the sum of this gives us the emitter current. So we can substitute this into here, and I will do it right now so to make things easier. So now I can write IC times, and I can say 1 plus 1 over beta, and the whole thing times RE. There we go. And what's happened now, what now happens is that the IC is here, here, and here. So we can cancel IC, and we will get the following equation. Okay, so we can say that we have only minus RC up here, we have 1 over GM down here, we have plus, and then we have, let me just write it that way, RE times 1 plus 1 over beta. There we go. And now we can simplify it even more, because what is a 1 plus 1 over beta? So for example, if a beta is very big, so let's say 300, then this here will be quite small, so this will be almost 1. So we can simplify this thing down, let's say simplified down to just this equation. We can just remove this completely like this, and we can simplify it to this. And this equation, of course, is the gain equation for the common emitter amplifier, or for the degenerated common emitter amplifier, because if this resistor is here, then we have to use this equation. And the thing with this is, if we short out the emitter resistor with a capacitor, then this here will go to 0, so we have plus 0, so we have only RC over 1 over GM, and this is RC times GM, of course minus RC times GM, and this would be the gain if there's no capacitor in here. Now let's look at this thing, let's analyze it without the equation. So now we already know that if there is an emitter resistor, the gain decreases because of this equation down here. And if we know if it is shorted with a capacitor, then we have the maximum gain. And depending on how big this resistor is, we can adjust the gain. But why is this actually working? The thing is the following. If we look carefully at this circuit, then the collector current depends on GM and V pi. So GM is the transconductance of the transistor, which is fixed at a specific operating point and a specific temperature. And V pi is the voltage between the base and the emitter. And the voltage between the base and the emitter is actually the difference of the input voltage and this voltage here across RE. Alright, interesting. So we have a voltage difference, so this voltage minus this voltage, which gets multiplied by some gain, and then we produce a current which later on gets converted into a voltage. So this is what we already had before in our operational amplifier. We had a different a voltage difference, multiplied it by some gain, and then we got an output voltage, which this construct is pretty similar already. So the thing with this now is that the current flowing down here, alright, is almost the same current. So the base current, we can neglect this now, so this is almost the same current. So if this resistor gets bigger, in ratio to this resistor of course, then we get, since the current is the same, we get more voltage drop on this one. So this subtraction action which is going on here, so we have harder feedback, so to speak. Okay, so this voltage here gets bigger, so we have more subtraction action going on here, and this of course will decrease the gain. Alright, very interesting. So this whole thing can be viewed as a feedback system of some sort, because we have a voltage on the output which gets fed back via its current somehow, and then we have a voltage here, it gets subtracted. So actually this seems to be a little bit like a differential amplifier or like a feedback amplifier. So let's have a closer look at the feedback structure of this thing, and then we should gain enough confidence to build this thing actually, to build actually a differential or an operational amplifier with just one transistor. So let's look at the feedback structure of that thing. So now we want to look at our common emitter amplifier from a feedback point of view. So I've redrawn the common emitter amplifier here, and I've simplified it a lot. I've just removed the bias resistors because I just want to have the core, the essence of the thing, and the essence is that we have an input voltage, output voltage, and two resistors. So we have V in here and V out here to ground. There we go. Okay, and before we start looking at this as a feedback system, first of all let us draw a simple feedback system. So if we have an amplifier which has an open loop gain, I call it AV open loop, OL. This thing has an output. Now this has no feedback already, but now if we use the output and if we feed it back to the input somehow, but first of all we maybe attenuate it with something. The attenuation of this or this feedback network is very often called beta, but I don't want to use beta because it's already a current gain, so I just call it beta F. Alright, and the output of this gets then subtracted from the input signal. So this is our input signal, which is V in. Okay, so the difference between the feedback, between the signal which we get from the feedback network and the input signal, I call this error voltage. So I call it VE, like error voltage, and I call this voltage just VFB, like feedback voltage. So this gets subtracted from this and then gives us this error voltage right here. And we have, of course, we have an output, I call it V out. How can we get the gain of this thing? Actually, let's see. How big is this error voltage? How big is VE? VE is V in, the input voltage, minus this feedback network, beta F, and output voltage times this feedback network, because output voltage times this gives us this voltage here on the minus, and the input voltage is here, so we have input voltage minus this gives us the error voltage across this point here. Okay, let's see how big is V out from a perspective of this amplifier. So V out is just VE times AVOL. There we go. And so that we know that, we can already write a simple equation, because we know VE, we can put the two things together, so we can see V out is equal to VE, which is this, V in minus beta F times V out, and the whole thing times AVOL. There we go. and we need to rearrange things so that we get V out over V in. And if you do that, you can multiply this out, and I will just write the final result, which I call V out over V in, and this is, oh sorry, let's make it a bit straight, AVOL, the open loop gain, divided by 1 plus beta F times AVOL. Okay, so this is the rearranged, just have to rearrange, just multiply it out and then rearrange it so that you get that you get this result here. Okay, pretty interesting. So how did this feedback network, or this system of this feedback system has such a gain? So we have an open loop gain, and we divide it by 1 plus beta F times the open loop gain. And if the open loop gain is pretty high, we can neglect it, and then we just have 1 over beta F. Okay, so this is what happens in operational amplifiers very often. So the next thing here is to derive an equation for our transistor amplifier, so to view this thing as a feedback amplifier. Okay, so now I need to rearrange things, so I will move this up here. So V out over V in is equal to AVOL divided by 1 plus beta F times AVOL. And now I can remove the stuff down here, and now we have to view this thing as a feedback system. Okay, so how does this work? Actually, do we need the equivalent circuit again? Maybe. Okay, now let's derive beta F of this circuit right here. So for this we need to know V out in terms of resistors and currents. So V out is, like we had it before, V out is equal to minus RC times IC. And we need to get the emitter voltage across here, so I call it VRE, and this is RE times IC, and since we have also our base current in here, it will be 1 plus 1 over beta, which we can neglect later on. So it's, of course, it's just RE times IC if we neglect the current gain, or if we neglect the base current. And our beta F will be the ratio of the output voltage to the voltage which is fed back via the emitter resistor. Alright, so again, our beta F will be the ratio from the output voltage, which is on the collector resistor, to the emitter resistor. Okay, so this is why I derived these two voltages here, and so therefore our beta F is the ratio of VRE to V out. Okay, so why? Because here we have V out, our feedback voltage here is in our case our VRE at this point, so I can call it VRE in our case. So our feedback network, of course, every network or attenuation thing has, so the gain of this network is output divided by input, and the output of this is VRE and the input of this is V out. And what is this? This is minus, and this is important. Our feedback network has a minus in it because of this, because RE is actually in the current is flowing in this direction, the output voltage goes in this, as mentioned before. We have this minus here, so this minus stays, and this is then VRE is RE times IC, and V out is minus RC times IC. Okay, and we have IC up here and down here. Sorry. I've wrote the minus here, so this is the minus, and we have IC up here and down here, so this is just minus RE over RC. And if we can get the open loop gain of the amplifier somehow, then we can get the closed loop gain with this equation here. And now let's see how can we get the open loop gain. So the open loop gain is the error voltage times this amplifier here. Okay, so the error voltage is the difference Vin minus VRE. So if Vin is here, VRE is here, then this will be the difference. The voltage V pi will be the difference. So this error voltage is actually V pi. Okay, so this is this. Great. So now that we know that, we might be able to redraw this and see the open loop gain. So we give it a voltage here and we get an output somewhere else. So actually the thing is now pretty simple. We just need to compute the gain from here to the output. So I can redraw it in the following way. I just say that here is my V in, then I still have an RE here. Well, no, I don't call it V in because then it's confusing because it's not V in. I still call it V pi, sorry. Then we have an RE here. We have our R pi here. Here we have our controlled current source. And this closes the loop like this. And here we have RC. Okay, and now it's interesting. So RC and RE is in series, and we have a voltage controlled current source here. So basically RE is doing nothing if you view it in the open loop view, because it's just in series. It's the same current here. So we have a voltage drop here, we have a voltage drop here, but this does nothing. So therefore we can conclude that our AV open loop is just minus GM times RC, because because V pi times GM gives us this current here, and to convert the current back into voltage we have this resistor. So therefore we multiply it with this resistor here, and because of the inversion we have the minus. Alright, so now how big is the closed loop gain? And for this we have to plug in the values right here, and we can see V out over V in is equal to AVOL was minus GMRC, and then we have 1 plus beta F. Where do we have our beta F? Beta F was minus, okay, minus, so we have a minus here, we have a minus here, minus RE over RC, and then we have our open loop gain again, which is also minus, so this becomes a plus again, GM times RC. There we go. So this here gives us now the closed loop gain of the circuit. So first we see that RC cancels out here and here. So we still have GM times RE, and we have 1 plus this. And if we divide it by GM, then we get minus RC 1 over GM plus, and GM cancels, so we have RE here. There we go. So this here gives us the closed loop gain, and this is exactly the same which we have derived before using just KVL and KCL, and now we have looked at it as a feedback amplifier, and we got the closed loop gain this way. So this proves the fact that this thing is indeed a feedback amplifier, and we can look at this thing as a feedback amplifier. So the only thing that's left is we have to figure out the way how can we connect 2 input signals to make our simplest op-amp in the world. So for that, actually everything is clear already. Let me just draw how we have to hook this thing up so that it works as the simplest op-amp in the world. So I just remove this here. Okay. So the only thing we have to do, to get our V pi, to get our voltage difference. So again, just to remember you, we have our normal operational amplifier, and it amplifies this difference between here, so with V in 1, V in 2, and we already have our V in 2 input actually, which is the base. So if we now, this is the final circuit, now this is our simplest operational amplifier, and we connect our V in 2 to the base, okay, and our V in 1, which is the non-inverting input, we will connect it to the emitter, because this is the non-inverting input, because we had this V pi and this is the subtraction going on in here. And so we just connect the V in 2, the V in 1 to the emitter. Okay, and now we have to take care for the bias. So resistors here, resistor here, here capacitor because of decoupling of the, here capacitor for the output, and here capacitor. And this is V out here, and this is the world's simplest operational amplifier. It's just basically, it's a common emitter amplifier with an extra input at the emitter, and you can view it in a different way. Basically, if you remove this here and if you connect this to ground, because if you connect, if you remove the voltage source, then it will become AC ground, so you have to ground it. Then you have a common base circuit. If you connect this to ground, then you have a common emitter circuit, and the common emitter circuit is inverting from here to here, so V in 2 is the inverting input. The common base circuit is non-inverting from here to here, so V in 2 is the non-inverting input of this thing. Alright, okay, so now let me write the simple equation for this, so we understand it better. So how big is V out? V out is, as we have derived it before, in terms of V pi, so V pi, the voltage here. Again, we have small signal now, so this is not the base emitter voltage, which 0.7 or 0.6 volts, we have small signal V pi. So it's V pi times, and the current here, so to get the current we have to multiply it by Gm, and to get the voltage we have to multiply it by RC, and since this voltage is reversed, we have a minus as we had it before. So this is actually the differential gain of this thing. And now let me fill in some voltages, so we can say that this V pi, what is V pi? V pi is V in 2 minus V in 1, of course, because we have V in 2, this here, minus V in 1 is this here, so this gives us V pi. And if we plug this in, then we can say that V out is minus RC times Gm times, and now V pi, and V pi is V in 2 minus V in 1. Okay, and now we can rearrange things. So we can write V out is equal to, and now I can put the minus into here, so I say positive RC times Gm times, and now I just have to reverse this, V in 1 minus V in 2. Alright, so this is the differential gain of our simplest operational amplifier in the world. So the differential gain is just RC Gm, and here we have the voltage difference, V in 1 minus V in 2. So now we have derived all equations of this, of the simplest operational amplifier in the world, and in our example, I will build it now on the breadboard, and in our example later on we will measure this current here, this IC, this operating point current flowing down here, and with this current we can compute Gm, because remember Gm is equal to IC over Vt, and if we compute this and multiply it by RC, then we will get our differential gain, and then we can measure both input voltages and subtract them and see if the output voltage corresponds with the difference of the two input voltages. So let's get right into it, and now let me build it on breadboard and show you what it does. Alright, so here I built the thing on breadboard for you so that we can experiment with it. And what I did here, so this section here is the world's simplest operational amplifier, and here we have a buffer stage because I use one function generator as input, and I will use two potentiometers to adjust the two inputs, to adjust the level of the two inputs. These are these two potentiometers. Then I will buffer them with this operational amplifier here, and then I will put them and connect them to the world's simplest operational amplifier and see how good it works. So one note here is that of course you don't have to use an operational amplifier to supply your world's simplest operational amplifier, because then it would be rubbish if you need an operational amplifier to supply a thing which should then act as an operational amplifier and should replace it. This is just because at the emitter of this transistor we have a low impedance point, and at the base we have a higher impedance point, and so that this output here has a low impedance so that we can drive enough, we have enough drive. I use this operational amplifier. But if you design this thing in a circuit, then you have to make sure that you just use one transistor and that you just use the right impedance levels, and therefore you don't need this thing here. It's just for the experiment. And the setup is here. So here we have the transistor, we have the inverting and non-inverting inputs. Here we have our collector resistor, which is 4.7 k ohms. And for the output, I've decoupled the collector resistor with this capacitor, and then we have this 100 k ohm resistor to ground. And this is here to remove the DC offset. So I decouple it here, and then the capacitor will charge via this resistor, and this will remove the DC offset. Because I use more than 2 channels, and the oscilloscope which I will use right now has only the AC coupling for the first 2 channels, but for the third channel I need to implement AC coupling manually. Therefore I have this extra thing in here. Okay, so but this is the circuit, and now before we start measuring it, let us just compute the gain of it. And we can easily compute the collector current, but we can also measure it accurately. So I will measure the collector current of this thing, because the collector current is what gives us the GM. So I will measure this accurately with my multimeter. So for this I have to set it to current mode, and since I'm expecting a pretty low current, which is about a milliamp, I can use the microamp scale, because this goes up to 4000 microamps, and 4000 microamps is 4 milliamps. This is more than enough. And now I will open up the circuit right here like this and turn on the power supply. So now let me measure the current. So for this, let me see if I can do this on camera easily. So here, and there you go. How big is it? It's 1.05 milliamps, so 1050 microamps, like goes down. But okay, but I will stick by 1.05 milliamps. So with this, now we can compute our differential gain, and then we can measure it if it is right or not. Alright, so now back to the whiteboard. So now we can compute the open loop gain of this thing. So now we know our collector current is 1.05 milliamperes. Therefore we can compute our GM with this equation right here, which is the collector current, which is well, let me just put it into the calculator. So we have 1.05 milliamperes divided by 26 millivolts, and this gives us 40.38 millimoles. So sorry, millimoles, there we go. So we have 40.38 millimoles. Millimoles is 1 over ohm, so you can call it millimoles or moles, or you can call it Siemens or ohms. So but this is millimoles, so moles is 1 over ohms. Strange, but this is how you can call it. And with this we can compute the gain of the thing. and the gain is RC times GM. The open loop gain is RC times GM. But don't forget something, we have connected to a resistor to the output here, which is R, if this is RC, just call it RL, and this was 100K, this was 4.7K, so we can almost neglect it because this is much bigger than this, but since I want to have it accurate, I have to include it in the computation, and I have to parallel these two, so I have to parallel 4.7K with 100K, and this is pretty simple. I just have to use 4.7K times 100K divided by 4.7K plus 100K. Okay, so there we go, and the total resistance here is in this case 4.489 K ohms, and I have to multiply this with GM with the 40.38 millimoles, and what do I get? Sorry, this is not very good. So, and what do I get from that? Just multiply it by 40.38 millimoles, and we get a gain of 181.26, or just round it off here, 181. So this is our open loop, our differential open loop gain of this thing, and now let's measure it. Now let's see if we are accurate and how accurate we are. So keep that in mind, 181 is what we are aiming. Okay, great. So now we are back at our circuit, and as I told you before, we have our two inputs, the inverting and non-inverting input, and we have our output. So these are the two channels of the oscilloscope. So actually the first channel of the oscilloscope is connected to the non-inverting input, okay, which is the emitter in this case, and the second channel of the oscilloscope is connected to the inverting input, which is the base in this case, because you can remember inverting input, it's the base, and therefore it's common emitter, and therefore it's inverting. Non-inverting input, it's the emitter, and in this case it's common base, and therefore it's non-inverting. And the fourth channel of the oscilloscope is now connected at the output of this thing. Okay, alright, here we're looking at the oscilloscope. So the inverting input is connected on the second channel, and the non-inverting input is connected on the first channel right here, okay. And the output of the world's simplest operational amplifier is connected to the fourth channel, which is currently disabled. And first of all, I will turn on bandwidth limitation on this oscilloscope just to get rid of high frequency noise so that we get a clearer picture. And I can enable it without any problems because this is only 10 kilohertz. And now if I adjust the potentiometer, which is therefore adjusting the non-inverting input, you can say I can easily adjust the non-inverting input like this, okay. This is great. And by the way, I use a multi-term potentiometer so that I get more precision adjusting this input. And now I will turn on the fourth channel to see the output. So this is the output of the amplifier, and as you can see, it's already quite big because we have 1 volts per division, and it is 4 volt peak peak, about 4 volt peak peak, okay. And now I will turn on the non-inverting input of this amplifier. So let me see, there we go. And now I decrease the level on the non-inverting input, and as you can see, the output decreases. The output reacts as it should, you can see. And if I increase it, then of course the output increases, and I can decrease it further and further. And if we reach the point where the inverting and non-inverting input has the same level, then of course the output is 0. And this is what we would expect from an operational amplifier, because it only amplifies the difference, and therefore we have built a pretty good operational amplifier just with 1 transistor. Isn't that amazing? I would say that it is. It certainly is. We have built an operational amplifier with just 1 transistor. This is just great. So now let's see what happens if I decrease the non-inverting input, and if it gets lower than the inverting input. Let's have a look. Decreasing, decreasing, and there we go. the signal flips around, and this is because now the inverting input wins. The inverting input has now more signal, and therefore the output is inverted. And this is of course a behavior which we would expect from an operational amplifier. So this is just great. It works exactly as expected. Isn't that amazing? So now, and we can flip it again, and there we go, and again and again. And of course we can adjust the non-inverting input and do the same. Alright, this is just great. This is just great. I really enjoyed it. Okay, so we have built a pretty good working non-inverting operational amplifier. Of course the open loop gain is much less than a real operational amplifier would have, but it can be good enough for some applications. So let's see how high the open loop gain actually is if we have computed it correctly, and how much our computation is off. So for that I will adjust it in a way that the output is about 1 or 2 volts peak peak. So now we have the output at 2 volts peak to peak. Yes, and now what I will do now is I will measure the voltage difference between the first and second input to get the open loop gain, because we have the difference times the open loop gain gives us the output. So since we know the output, we have to measure the input difference divided, and we get the open loop gain. So for this I switch off channel 4, and now we have only channel 1 and 2, and now I have to subtract channel 1 from I have to subtract channel 2 from channel 1 to get the difference. And on an analog oscilloscope like this, or at least on most analog oscilloscopes, you do it in the following way. You just add both channels. So now we have first plus second channel, and then I invert the second channel. So now I subtract the 2 channels, and now I can zoom in a bit. Okay, so but this is now the maximum because I have 10x probes, but it's good enough for this example now. And here the cursors are already positioned quite well, but let me do it a bit better. There we go. So our output voltage here is now 12 millivolts. Alright, so now let's compute the gain. The gain is now the output voltage divided by the voltage difference, which is 0.012, and this gives us 166. So we have a gain of 166. We have computed it with about 180. So this is close enough, because I cannot actually, it's not so easy to measure it. So actually this is close enough. So our simplest operational amplifier works as expected. It works pretty fine. So I really like this. I put it back to where it was before, and as you can see, I can still play around with it, and there we go. It's just amazing. That's a joy. That's just amazing. That's happiness. Look at that. It's just great. Okay, so this concludes this oscilloscope session. Okay, so there you have it, the world's simplest operational amplifier. And before I conclude this video, I want to show you that this thing is a real thing, and I want to show you some example of the world's simplest operational amplifier. So let's have a look at some circuits, maybe in some books and other stuff. Okay, alright, so here we have a book about transistor circuit design, so I'm pretty sure that we can find the world's simplest operational amplifier in this book. Let's see if we can find some examples in here. So let's see, maybe here. Oh yeah, there we go. So here we have it, another implementation of the world's simplest operational amplifier. This is a video amplifier, integrated circuit video amplifier, so this is part of an IC, part of a chip. And also in here we have it, because this is the output. Okay, this is the first gain stage. Alright, so here we have the input, okay, and the output here is fed back to the emitter at this point, and therefore the output gets subtracted from the input voltage in that way, and therefore we have again the world's simplest operational amplifier in here. this thing, keep in mind that this thing has an extra inversion going on here, because here we have this stage, so we have one inversion here and it's inverted back here. So therefore we have to switch the polarity basically, because before this was the inverting input and this was this was the inverting and this the non-inverting, but now it's the other way around. Now this is inverting and this is non-inverting because of this second stage here, but the concept is still the same. Okay, alright, so let's look at another example. Okay, alright, here we have another book about electronic circuit analysis. If you like differential equations, then this is the right book for you. And I'm pretty sure that we can find the world's simplest operational amplifier in here too. Let's see, let's have a look. Okay, there we go. Also on this page we have the world's simplest operational amplifier, but this time in vacuum tube form, and this is also not a problem because you can build it with vacuum tubes, of course. So where is the subtraction going on? It's again on the first stage here. So here we have our input on the grid of the vacuum tube, and on the cathode here comes the feedback from the output. So it's the same configuration as we had before with this video amplifier thing. We have two inversions, therefore this here is the inverting input and this is the non-inverting input of the whole thing. Here we have the output, it's fed back via this resistor, and we get our world's simplest operational amplifier also in this practical example. Great, so let's look at another one. And since we are starting to look at vacuum tube circuits, we just cannot neglect the Radiotron's Designer's Handbook, and it's just impossible that there is no world's simplest operational amplifier in here. So there must be a world's simplest operational amplifier in here. This is just it has to be. Okay, and now just let's have a look, and I'm pretty sure that we can easily find one. So let's see what we have in here. Okay, this looks promising. There we go. All right, so there you have it here, right in the middle. So let me zoom in on that. And here we have another implementation of the world's simplest operational amplifier. Actually, it's pretty much the same as before. We have this subtractor stage here. So we have, this is a triode. On the grid we have the input as a non-inverting input, and on the grid and on the cathode here, the cathode goes with this resistor to ground, and then we have this feedback coming in here from the transformer. Since this is an amplifier with an output transformer, you can use the transformer to your advantage for the phase. So if it is inverted or non-inverted, can just be done via the transformer. So you don't have to take care how many stages or so, it's just done via the transformer, because this can decide if it is inverted, and then it's fed back right to here. And yeah, this is just another beautiful implementation of the world's simplest operational amplifier. Okay, so let's continue. So to round this off, here we have one page of a service manual of the Revox A77 tape recorder, and this is the line microphone amplifier of that thing. And if we zoom in here, that we can see we have another beautiful implementation of the world's simplest operational amplifier, even though it's a bit different in here. The amplifier here, this transistor is the amplifier. It's a bit more involved here, but we have an inversion going on from this point to the output point. Alright, so again we have the inverting input of this thing at the emitter. So this is the feedback loop. So we have here via this resistor it's fed back, and this is our resistive feedback divider, these resistors here, and our non-inverting input is connected to the base of this transistor. Alright, great. So here we have another implementation of the world's simplest operational amplifier, found in a Sony tape recorder. It's a Sony TC366, and this is another interesting tape recorder circuit. And right here you can find the world's simplest operational amplifier. It's hidden in here. it gets feedback at the emitter with this here, then this to ground, and its input is on the base. So again, we have another case of the world's simplest operational amplifier. Alright. Okay, so this concludes our study of the world's simplest operational amplifier, and the conclusion is that you can really build this with just one transistor. And if you want to go more advanced, then you can of course use more and more transistors, and it gets more and more complex, but then it gets better and better. So the one transistor implementation is of course not nearly as sophisticated like this chip here, but if you add more and more transistors, then it will get better and better. So you can play this until you reach a point where, yeah, you have to decide if you use the chip or if you use the transistor. So you have to decide what's better for your application. But the conclusion is that you can easily build an operational amplifier with one transistor, and you can go more advanced if you use multiple transistors. And this would be a topic for a separate video, to build a more advanced operational amplifier with just transistors, which has more features like the real operational amplifier has, for example, more open loop gain and such stuff. Okay, yeah, but this now concludes this video, and I hope that you have enjoyed watching this video and maybe learned a thing or two. And so I can say thanks for watching and bye!